we have a synapse being formed for memory. A connection is formed here. And here's our presynaptic axon, here's the synapse, here's the postsynaptic cell. Oh, sorry, yes.
That's okay. Would you just repeat what you said? The receptors trigger a depolarizing potential?
Depolarizing, excitatory, postsynaptic potential.
Okay.
Those two words kind of go hand in hand. Just remember that if we say something is excitatory, it must depolarize the membrane, right? Because we're trying to get to threshold to get an action potential. If we say something is inhibitory, it's hyperpolarizing the membrane, making it less likely to get an action potential. So we often abbreviate that EPSP for just excitatory postsynaptic potential. It's got to be depolarizing. IPSP, inhibitory postsynaptic potential, has to be hyperpolarizing. Okay? All right. Is that okay? Okay. So here's initially what happens. We have a neuron, presynaptic axon here, synaptic end bulb here. Action potential travels down, opens voltage-gated calcium channels. Calcium rushes in, changes the affinity of the docking protein. Vesicles bind to the postsynaptic cell membrane, or the axon cell membrane, and exocytosis. Right? You did all that yesterday. Releases the neurotransmitter. In memory, long-term memory, the neurotransmitter is glutamate. Are there other kinds of neurotransmitters? Yeah, there's 100 or so. This is one that's important in memory. Initially, ignore this right here, initially, this neurotransmitter binds to this receptor, AMPA here. Notice it's gated, so this would be a ligand-gated receptor. And it's a receptor linked to an ion channel, and the ion channel is sodium. So with no neurotransmitter, the gate's closed. You release the neurotransmitter, binds, the gate opens, and we get sodium influx. Now what does that do to the potential of the membrane? Depolarizes it, right? So this influx of sodium is going to depolarize. And depending upon what this is, well, since this is another neuron, right, that influx of depolarization would be sufficient enough to reach threshold, and we would get another action potential, and then it would go down to the next cell. Now, as we continue to use this synapse over and over and over again, the postsynaptic cell will respond to that by increasing its sensitivity to the neurotransmitter. How does it increase the sensitivity to the neurotransmitter? Just makes more AMPA receptors. Just make more of them. So now, if instead of one of them, I've got 4 of them here, we will get more rapid depolarization in the postsynaptic cell, right? That reinforces that synapse. Easier to get an action potential. You okay with that? Okay. As it keeps using it more and more and more and more, the postsynaptic cell even gets more sensitive by increasing or producing a new kind of receptor. And this new receptor is that one called the NMDA receptor. Now, this NMDA receptor is very different than this one. It's different 2 ways. One, it's gated, but it's gated because there's a magnesium ion stuck in the middle. I don't really care about that so much. That doesn't really change the story here, but it's not a physical little gate like we've talked about before. It's like when there's no ligand here, no neurotransmitter, there's a magnesium ion blocking the hole. Right? So it's just in the way. Okay, you okay with that? When the neurotransmitter binds to this NMDA receptor, it changes the affinity of this receptor for magnesium. It decreases it, right? So what happens to the magnesium ion? Falls off. Now the channel is what? Open. Now this is not a sodium channel, this is a calcium channel. And you get calcium influx. Now what does calcium influx do to the potential of the cell membrane? Depolarizes it even further and even faster, right? Because calcium is a +2 charge instead of a +1 charge. So you can see how as soon as you get these, in addition to these, we've got lots of AMPA receptors, lots of NMDA receptors. It's going to take a very little bit of glutamate to get a postsynaptic potential down here. Does that kind of make sense? So this is called long-term potentiation when that happens. Now what's interesting is think back back here. We had an influx of calcium here, right? Which triggered a release of the neurotransmitter. Now we've got an influx of calcium right here, right? Okay. Now, this is hypothetical, but I mean, they haven't identified what this paracrine is. But the influx of calcium actually causes a release of a paracrine from the postsynaptic cell. Okay with that? So, just like it did up here, calcium comes in, release paracrine. Down here, calcium comes in, release paracrine. And what does this paracrine do? This paracrine actually creates a positive feedback loop on the postsynaptic cell here. So this paracrine causes what? More neurotransmitter. More neurotransmitter, more calcium, more paracrine. More neurotransmitter. So this is a positive feedback loop, right? More. So this paracrine that's released here, again, reinforces this synapse by causing more neurotransmitter. So what did we get in this long-term potentiation? Because we used this synapse more and more, and it's meaningful, either consciously meaningful or subconsciously meaningful because it's being used repeatedly, we saw this is called upregulation, an upregulation of AMPA receptors. We saw via this positive feedback loop that's created a release of more neurotransmitter into the synapse. And then we saw the production on the postsynaptic cell membrane of a stronger, if you will, excitatory receptor for glutamate called NMDA. And that really reinforces that. Now, what's interesting is that is there around, I mean, just think around this room. I mean, this is not bad in any way, but think about people in this room. Do different of us in this room have different natural capacities to memorize things? Some people memorize things and learn things very quickly, right? Others, it takes longer. I'm one of the ones that takes longer. Okay, I don't have a really good memory. Okay, once I get something, though, I kind of get it and it stays with me, but it takes me a long time to do this process. There are people that do this process very quickly, right? You ever seen those people or known people that have kind of photographic memories and stuff like that? What are they doing, really? They're doing long-term potentiation a lot more rapidly, right? And is there natural difference